So in the last classes we were going through the bonding or in H2 plus molecular ion or bonding in hydrogen molecular ion. Okay, and we got some interesting results. We got the expression for two energy states. One energy state was represented as E plus, and that energy was HAA plus HAB divided by 1 plus S, and another energy was E minus, which was equal to HAA minus HAB divided by 1 minus S. Okay, and these energies were corresponding to two wave functions. This was corresponding to the wave function psi plus, which is equal to 1 divided by root of 2 into 1 plus s into 1 as a plus 1 as b, and E minus was corresponding to the wave function psi minus, which is equal to 1 divided by root of 2 into 1 minus s into 1 as a minus 1 as b. Okay, these were the two wave functions. And we also saw that and these two wave functions and their corresponding energy profiles, they lead to different bonding situations in the hydrogen molecular ion. For example, if we are plotting the energy, okay, energy versus internuclear distance, we will get the plots like this. Okay, we are plotting the internuclear distance in in this axis, and here we are taking the energy, and let me take this as the energy of the H hydrogen atomic orbital, and then I can see that if we are plotting E plus, okay, if we are plotting E plus, the plot of E plus will be like this. It will be like this. Okay, and if you are going for the plot of E minus, it will be like this. It will be like this. That is, this is a plot of E minus and this is a plot of E plus. And corresponding to the profile of E plus, we have a value here, or there is a minimum here, and the distance, internuclear distance corresponding to this minimum. Okay, internuclear distance corresponding to this minimum, that is this distance. Okay, and this distance is the equilibrium bond distance, and this was found to be 1.32 angstrom. Okay, and the energy from here to here was found to be around 1.77 electron volts. And if you are looking at E minus, the E minus always has an energy which is greater than the energy of the hydrogen atomic orbital. Therefore, we said that the molecule will always try to put its electron, the only one electron, obviously it is a one electron system, so the molecule will always try to put its electron in this E plus profile, especially in this molecular orbitals. Means the electron, the only one electron which is present in the hydrogen molecular ion, will always try to occupy the psi plus molecular ion. Okay, psi plus molecular ion. And if it is occupying the psi plus molecular ion, then this will occupy in this stage, okay, where the internuclear distance is 1.32 angstrom. This is a calculated value. Obviously, you have to remember that this calculated value is different from the experimental value. Anyway, I already said in the beginning itself that we have done all these things with a trial wave function. Therefore, there is a chance of error. There is a scope to improve improve these values if you are choosing better trial wave functions. Okay, so whatever it may be, we are discussing the whole system with the calculated values. So the molecule will try to attain a configuration in such a way that the two nuclei will be at a distance of 1.32 angstrom, and in that case the molecule will be in this state, with the state represented by this point. Means the molecule will be in the valley of this curve. Okay, and therefore the molecule will be stable because it's at that time the energy will be less than the energy of the hydrogen atomic orbital. So molecule, it is a stable system. The energy is being saved. So we say that this is a bonding molecular orbital. This is a bonding molecular orbital. Okay. But if you are considering the other case where E minus having E minus profile, we can see that the molecule will always have the energy which is greater than the energy of the hydrogen atomic orbital. So this molecular orbital will always have a energy greater than the hydrogen atomic orbital. Therefore, if the electron is going to sit in the orbital corresponding to E minus, means if the orbital is going to sit in psi minus orbital, then it is leading to an unstable state. Means because the molecule would have an energy if it was staying in the hydrogen atomic orbital, and after forming the molecule, then it is being pushed to stay in a higher energy orbital, psi minus. Then in that case the molecule will be unstable, or we can say that if the electron is promoted to the orbital corresponding to E minus, means if the orbital is promoting to psi minus, then the molecule will be dissociated. So this is the anti-bonding molecular orbital, anti-bonding molecular orbital, anti-bonding molecular orbital. Okay, so we already know this. And today we are going to consider about the symmetry of these molecular orbitals. Then we will go for some notations based on the symmetry of these molecular orbitals. Here you can look at the expression for the molecular orbital, the psi plus. This is 1s a plus 1s b, means 1s a is the atomic orbital of the hydrogen atom A, and 1s atomic orbital of hydrogen atom A, and 1s b is the hydrogen atomic orbital, the 1s atomic orbital of hydrogen atom B. And these two wave functions are being added up, and then it is multiplied by some value, that is 1 divided by root of 2 into 1 plus s. That is how we are getting the psi plus molecular orbital, right? So essentially what we are doing there is we are adding two atomic orbitals, 1s a and 1s b. Okay, so let us check what happens when these two atomic orbitals are being added. So this is the internuclear axis. Okay, and let me draw the points where the nuclei are occupying. Here the nucleus A is here, and here is nucleus B. This is nucleus B. Both of them are hydrogen nuclei, and 1s atomic orbital means the atom 1s atomic orbital of hydrogen atom A. That is a spherically symmetric atomic orbital. You already know this, right? So if we are drawing the 1s atomic orbital here, uh, then it will be like this. Okay, let me choose another brush to show this. So we are going to take the 1s atomic orbital here. It is a spherically symmetric orbital. Okay, 1s atomic orbital here. Okay, so this is 1s atomic orbital, and now we have to see what is 1s atomic orbital of the hydrogen atom B. That is also a spherically symmetric orbital. So we can draw the spherically symmetric orbital of the hydrogen atom B here, 1s atomic orbital, and 1s atomic orbital of hydrogen atom A and 1s atomic orbital of hydrogen atom B are equivalent. Okay, and it will be like this. It will be like this. So we have drawn the 1s atomic orbital of hydrogen atom A and hydrogen atom B, hydrogen atom B, and these two atomic orbitals are centered around the two hydrogen nuclei A and B. These are A and B. Okay, this is A, this is A. You can take another pen. So this is A and this is B. Okay, this is A and B. You cannot see that. I will write it in. Yeah. This is A, and this is B. Okay, now you can look what happens to this. What happens to the value of these wave functions when we are considering the molecular orbital, means the psi plus molecular orbital. In psi plus molecular orbital, it is 1s A plus 1s B, right? Means 1s atomic orbital wave function is added with 1s B. 1s atomic orbital of wave function of A is added with 1s atomic orbital of B. So if we are considering this position, means if we are considering the position in between the two nuclei, then we can see here, if we are considering this position, okay, if you are considering this position in between the two nuclei, here, here, here 1s atomic orbital of both A and B are there in this region, right? You can see the 1s atomic orbital of hydrogen atom B and 1s atomic orbital of hydrogen atom A also in this region. So from our expression, in order to get the molecular orbital, 1s A is added with 1s B. 1s A is added with 1s B. Here you have to remember that both 1s A and 1s B have the same sign, right? So if you are plotting the 1s atomic orbital of hydrogen atom A and hydrogen atom B, both of them will have the same sign. So suppose this is plus, okay, and this will also be plus. Both of them are atomic orbitals. They have the same sign. No matter no matter they belong to two different hydrogen atoms, but they have the same sign. Okay, so when these are added up in the internuclear region, then this positive wave function will be added up with the positive wave function here, so that you will get a double value of the wave function here, right? The double value of wave function in the internuclear region. So this is what is happening in the case of psi plus. In the case of psi plus, the molecular orbitals are being added up. Okay, in the case of psi plus, the atomic orbitals are being added up. So you have some number multiplied with 1s atomic orbital of A plus 1s atomic orbital of B. So addition of the atomic orbitals are happening in the internuclear region. So what is the result of this addition? Then if you are looking at this one, then you can see that the electron density in the internuclear distance will be increased because of the addition of the two atomic orbitals here. Okay, so the resultant wave function will have the double the intensity of the electron that we would actually expect. Okay, if you are considering only the atomic orbital, whatever may be the value of wave function that you have to expect here, okay, then double of that multiplied by some constant n here. Okay, that is equal to 1 divided by root of 1 into 1 divided by root of 2 into 1 process. Okay, so that is what is happening here. So the entire wave function will be added up, the two atomic orbitals will be added up in the internuclear distance. So that is why there will be build-up of the electron density in between the internuclear region, and because of this build-up of the electron density, what happens that the repulsive interaction between the two nuclei will decrease. Actually, what is actually happening is that this nucleus A will try to attract this electron density here, and nucleus B will also try to attract the electron density here. So instead of moving apart because of the repulsive force between A and B, അല്ലെ എയും ബിയും തമ്മിലുള്ള repulsive force മൂലം ആ രണ്ട് ന്യൂക്ലിയസുകളും പരസ്പരം അകന്നു പോകുന്നതിന് പകരമായിട്ട് then there is a force which binds them together in that place. That force is the attractive force between the nucleus A with the electron density and the accumulated electron density in the middle, and the attractive force between the nucleus B and the accumulated electron density in the middle. So that is why it leads to bonding. അല്ലേ, ഇങ്ങനെയാണ് ബോണ്ടിങ് ഉണ്ടാകുന്നത്. Therefore, the psi plus atomic orbital can be called as a bonding molecular orbital. Now you can look at the symmetry of this molecular orbital. So if you are drawing the molecular orbital here, it will be something like this. Okay, so we can draw it like this, just like this. So the point A is here, this is point A, and here is a point B, and the molecular orbital, uh, the electron density in the middle will be very high because of the addition of the molecular orbitals. So if you are considering the rotation of this molecular orbitals with respect to the axis which connects the nuclei A and B, this axis, okay. If you are rotating about this axis, ഈ axis about നിങ്ങൾ rotate ചെയ്യണമെന്നുണ്ടെങ്കിൽ, then what will happen? Actually, if you are looking at this orbital and rotating about this axis, then there will be no change in the appearance of the orbital. Okay, the appearance of the orbital is not going to change when you are rotating about this axis. അല്ലേ? അതുകൊണ്ട് നിങ്ങൾക്ക് ഇതിനെ cylindrically symmetrical orbital എന്ന് വിളിക്കാം. This orbital is cylindrically symmetric orbitals. Since it is cylindrically symmetric orbital, then you can call this as a sigma orbital. This is a sigma orbital. So instead of calling this as psi plus, I will call this as a sigma orbital. It's a sigma orbital. Okay, and you know that this sigma orbital is a bonding molecular orbital. Okay, so here the sigma orbital is the bonding molecular orbital, and it has a cylindrical symmetry also. Now we can look at the other orbital, other molecular orbital, that is the psi minus, that is 1 divided by root of 1 into 2 into 1 minus s into 1s a minus 1s b. Here you look at this one. This is 1s a minus 1s b. 1s a minus 1s b. This is what we have to look into carefully. Okay. So again, I am going to draw the picture here. So we have the 1s atomic orbitals here. Okay. Let me copy this to here. If we are going for the psi minus molecular orbital, it will be like this. Okay. Psi minus orbital, it is going to be like this. Here the difference is that here also we have the 1s atomic orbital of A and 1s atomic orbital of B, but you know that here it is 1s A minus 1s B, right? 1s A minus 1s B. 1s A, sorry, 1s A minus 1s B. Here we are multiplying 1s B atomic orbital with a negative sign, right? Therefore, instead of being plus, this will be negative. This is going to be negative. So this will be negative. This is minus. So this is plus here, and in the case of B, 1s B, it is minus here, because the sign of the atomic orbital is changed because of the expression of the molecular orbital, right? In the molecular orbital expression, we have 1 as a minus 1 as B. Since it is minus 1 as B, it is going to be minus. The sign of the atomic orbital is to be considered as minus here. So what happens in the internuclear distance, internuclear region? If you are considering the internuclear region here, then what we can see here, the internuclear region here the plus and minus comes together, right? So they cancel each other. So the result is that in the internuclear region there is a decrease of the electron density. Electron density is cancelled, or the wave functions are cancelled, okay, or a node is being created here in the internuclear region. A node is created. So that is what is happening here. So if the molecular orbital is this one, then if you are looking at the electron density of this molecular orbital, in between the nuclei, the electron density will be null, or electron density will be zero. If the electron density in between the nuclei are diminishing, or if the electron density in between the nuclei are decreasing, that situation corresponds to the anti-bonding situation. Means the nuclei are no more will be interested to kept together, because of the internuclear repulsion of the two nuclei, they will go far apart, and there is no force to bind them together because the electron density in between the nuclei are gone. Therefore, this leads to the dissociation. If the electron is filled in this orbital, that leads to the dissociation. Therefore, this is an anti-bonding molecular orbital. So this is anti-bonding molecular orbital. Anti-bonding molecular orbital. Anti-bonding molecular orbital. Okay. And now you can look at this molecular orbital. Okay. If we are rotating this molecular orbital, this molecular orbital also will be something like this. Let me draw this here. It will be like this. Okay. And the two nuclei are here. Two nuclei are here. This is nucleus A and this is nucleus B. And if we are considering the electron density will be far away from the internuclear region. Far away from the internuclear region. Okay. So in the internuclear region, there will be no electron density. So if we are looking at this point, which is the midpoint of nucleus A and nucleus B, in that midpoint the electron density will be zero. Okay, and you have to see that this is positive and this is minus, this is negative. Okay, in this case all was positive. Okay, so this is positive and this is negative, and there is no electron density in between the two positive and the negative parts of the wave function. Okay, or between two lobes of the molecular orbit. There is a notch. There is a notch. Okay. So if you are rotating this one about the axis AB, then what you will see, whether the appearance is going to change or not. In fact, not, because these are cylindrically similar. Even if we are rotating about that axis, you will see the same thing. Okay, the appearance is not going to change. Therefore, again you can call this as a sigma orbital. Since it is cylindrically symmetric, again you can call this as a sigma orbital. But you have to remember here that this is an anti-bonding molecular orbital, right? If the electron is sitting in this molecular orbital, that leads to the destruction or dissociation of the molecule. So this is anti-bonding molecular orbital. Since it is anti-bonding molecular orbital, we call this as sigma star. Okay. So if you see the star also with this, you have to consider this as anti-bonding molecular orbital. If there is no star, if the star is absent, then it means that is the bonding molecular orbital. So we have two molecular orbitals here, the sigma molecular orbital and sigma star molecular orbital. Sigma molecular orbital and sigma star molecular orbital. Okay. And since both of them are formed from the 1s atomic orbitals, see, whether it is sigma or sigma star, both of them are formed by the linear combination of the 1s atomic orbitals. Here it is 1s A, 1s A plus 1s B combination. Here it is 1s A minus 1s B combination. Both are the linear combination of 1s atomic orbitals. Therefore, we can call this as sigma 1s and this as sigma star 1s. So we have two molecular orbitals, and based on their symmetry, we have named them as sigma 1s and sigma star 1s orbitals. So in the case of the hydrogen molecular ion, either the only one electron in that molecular ion can sit in the sigma 1s molecular orbital. Otherwise, it can sit in the sigma star 1s molecular orbital. If it is sitting in the sigma 1s molecular orbital, this is going to lead to a stable configuration, so that the molecule is going to be stable. But if it is promoted to the sigma star molecular orbital, then it is going to be unstable. You already know that the sigma star is having a higher energy, so its sigma star's energy is somewhere here. This is the molecular orbital sigma star 1s, and sigma 1s has a lower energy, so this is sigma 1s. So molecule generally will try, the electron generally will try to occupy this molecular orbital. If you are giving sufficient energy, for example, if you are giving a photon of this energy gap from here to here, okay, then this electron will excite to this molecular orbital to here, okay, then it will excite to here. Let me draw it in the red color. So it will excite to this into this one. Once it is excited to here, then it will occupy the antibonding molecular orbital. So the molecule will immediately dissociate. Okay, that's what's going to happen. That's what we can understand from this molecular orbitals of the hydrogen molecular ion. Okay, and now we have to again consider some more symmetry aspects of this molecular orbital ion. Now we know that this is a diatomic molecule constituted by the same atoms, okay, H, right? So if the diatomic molecules are constituted by the same atoms, obviously they will have the inversion center, right? You know this already, you have learned this from the group theory. Or if you are considering Cl, so it will have an inversion center, the middle of the chlorine-chlorine bond. If you are considering the N2 molecule, okay, nitrogen molecule, then it will have an inversion center in the middle of the bond, right? So in the middle of the bond, there will be an inversion center. So if you are considering an oxygen molecule, then also there will be an inversion center in the middle of the bond. What is the meaning of that inversion center? It means that if you are drawing a line, from the inversion center to any part of the molecule, you are drawing a line to here, and it meets an oxygen atom here. And then you are extending the line from this inversion center to the other side. Then it meets the oxygen atom at the same distance. If you are looking at this distance and this distance, the distance will be same. Okay. So if you are bringing this oxygen to here and bringing this oxygen to here, and that is not going to change the appearance of the molecule, then you can say that it has an inversion center. Same is the case with all the homonuclear diatomic molecules. Same is the case with H2 plus also. Here H2 plus is also made up of two hydrogens. The only thing is that you have one electron striked off from the molecule, right? That doesn't matter. Even if one molecule is striked off, that electron is uniformly distributed between the two hydrogen nuclei. Okay, so it has an inversion center here. This molecule has an inversion center here. So if you are drawing one line from here to here, and then you are drawing the line from here to the same distance, it will meet the same points, right? So it has an inversion center. Since it has an inversion center, we are going to operate this inversion symmetry in the molecular orbital. So we can see what will happen if we are operating the inversion symmetry to these molecular orbitals. For example, we are drawing an inversion. We are performing an inversion symmetry here. Our inversion center is here. Let me draw that in another color. So this is inversion center. Where is it? Yeah, here is it. This is inversion center here, and here this is inversion center here. Okay. So if I am drawing a line from here to any part of this orbital, let me draw this line to here. So it reaches this point. Okay, it reaches this point here. Let me call this as point 1. Okay, point 1. And then what I am going to do, I am going to extrapolate this line to the other side. I'm going to extrapolate this line to the other side, to the same distance. Then it reaches this point, right? It reaches this point. And let me call this as point 2. And now what I am going to do is I am going to see the value of the wave function at point number 1 and point number 2. And you know what is the relation between the point number 1 and point number 2. Point number 1 and point number 2 are in a straight line, which also includes the inversion center, right? So, and also the distance of the point number 1 from the inversion center is equal to the distance of point number 2 from the inversion center. That's the relation. So from the inversion center, this point number 1 and point number 2 are at the same distance. Now we are going to measure the value of the wave function at point number 1 and point number 2. So in the case of the sigma 1 as molecular orbital, I am going to see what is the value of the wave function at point number 1. Okay, and that was psi 1. Okay, psi 1 was the value of the wave function here. And now I am going to estimate the value of wave function at point number 2, and that was equal to psi 2. Okay, psi 2. That is the value of wave function at the other point. Now, if I am checking these two expressions for the wave functions, I can see that psi 1 is equal to psi 2. This is obvious. Both of them have the positive sign and they are symmetric. So whatever may be the value of your function here, it will be equal to here. So psi 1 is equal to psi 2. Okay, since it has this inversion symmetry. Okay, or when we are performing the inversion operation, since the wave function has the same value at both points, we can call this as gerade. Okay, it is written gerade. Actually, it is a German word. R is silent here, so we have to read it like gerade, gerade. Okay, it means that straight or same. Okay, means psi 1 is equal to psi 2, and you can perform this operation with n number of points in these molecular orbitals everywhere. So wherever you are performing this operation, you can perform like this. Okay, maybe like this. Wherever you want, you can perform. You draw a line from the inversion center to any point in the molecular orbital, and then you extrapolate that line to the other side to the same distance, and then check the value of the wave function to 2 points, and you can see that the value of the wave function to 2 points will be the same. And in that case, you can say that this is a gerade orbital. Okay, means the wave function's value will be the same in all the cases whenever you perform this inversion symmetry. Since it is a gerade orbital, you can call this as sigma g orbital. So sigma g orbital. We call this as sigma 1s orbital. Now we call this as sigma g 1s orbital. And sigma g, in sigma g, g represents it is gerade. Okay, many people read it as gerade or gerade or whatever it may be. Okay, the people from different linguistic background may read it differently. That's okay, no problem. But exactly speaking, the German should call this as gerade. Okay. So this is a gerade. This is a orbital with the gerade symmetry. Okay, so this is sigma g 1s orbital. And if we are looking at the other one, this one, here also we do the same thing. Okay, I am going to draw a line from the inversion center to some point in the molecular orbital to the left hand side of the molecular orbital. Then I identify the point number 1, and then I am extrapolating that line to the other side, and I am getting the point number, identifying the point number 2, and then I find out psi 1 and psi 2, psi 1 and psi 2. Okay, and I can see that psi 1 and psi 2 may have the same value, the expressions are going to be the same, but there is a difference. Uh, Psi1 may be positive, but Psi2 will be negative, because you already know that this is having the negative sign all over here in this part. It has a negative sign. So Psi1 is equal to minus Psi2. Okay, Psi1 is equal to minus Psi2. And in this case, we can say that it is ungerade, okay, or ungerade in German language, ungerade, ungerade. Since it is ungerade, you can call this as sigma star u, okay, sigma star u. So this is sigma g and this is sigma star u. Okay. So we have two molecular orbitals, sigma g 1s and sigma u star 1s. Okay. And these notifications came there from their symmetry aspects. So now you understand what is meant by sigma g 1s molecular orbital and sigma u star oneness molecular orbital. Okay, so this is the ground state. If the molecule is sitting in this molecular orbital, then we can say that the molecule is in the ground state. And if the molecule is sitting here, molecule means the electron. If the molecule, the electron is sitting here, then we can say that the molecule is in the excited state. Obviously, the excited state of this molecule is highly unstable. It is going to dissociate. Or you understood the notations of these molecular orbitals, okay, from the symmetry aspects. If you understood, I am going to wind up this session. If you did not understand, you can contact me as I am saying always, okay. So we have the molecular orbitals sigma g and sigma u star. And thanks for watching, and see you again.